So, yes, I'm going to speak about small-scale atmospheric processes in a warmer world, but actually I'm going to speak about thunderstorms in a warmer world. And as we've just heard from Dietmar, convection and clouds are fundamental to understanding how the future climate will work. We also heard from Andy yesterday about why the land surface processes matter to the atmosphere. And I think caught up with land surface is convection, and convection also matters really fundamentally to the future climate. So I'm going to talk about some large-scale climate projections of mean and extreme rainfall, which is not really my area of expertise. I'm then going to give a brief review of what thunderstorms are and how they form. I'm then going to talk about mesoscale convective systems in the MJO, and finally look a little bit on how model resolution and convective parameterizations impact on convection in our understanding of weather and climate. So the IPCC AR5 report states that there are likely more land regions where the number of heavy precipitation events has increased than where it has decreased. Recent detection of increasing trends in extreme precipitation and discharge in some catchments implies greater risks of flooding at regional scale. So although our climate model projections of the future climate are based on mean rainfall, we definitely have some hints coming through in the IPCC reports about extreme rainfall. And generally when we're talking about extreme rainfall, we're talking about convective events. So you saw this plot from Dietmar. This is the change in average precipitation for the late 21st century relative to the late 20th century for RCP 2.6 and 8.5 scenarios. And so we've got this moistening through the tropics and drying through the mid-latitudes. But you can see these patterns are rather smooth patterns, and there's not a great deal of regional variation. And for the future, the report makes statements like changes in precipitation will not be uniform, extreme precipitation events over most of the mid-latitude land masses and over wet tropical regions will very likely become more intense and more frequent. So we're seeing lots of words that are alluding to the frequency of convection in the future climate. So as we heard from Dietmar, in a warmer world, we have a warmer temperature, greater water vapour mixing ratio, and more rain. However, we know that precipitation is one of the most locally controlled atmospheric variables. So this is just a climatology of rainfall in the maritime continent region, which is the tropical region right to the north of Australia, extending from Sumatra over here across to New Guinea over here. And just in this small plot, we can already see orographic effects. So this is average rainfall, but we can see peaks in rainfall along the slopes and tops of the topography. We can see coastal effects, where the effect of the land extends far offshore. It can extend more than 800 kilometres from the shore. And we also see the effect of local circulation, such as the Borneo vortex in here. So these are all things that are not really going to be captured in a GCM. And particularly in a region like the maritime continent, where we've got this complex archipelago of islands and water, almost all of the region is somehow affected by these coastal land-based processes. And these strong variations, these strong land-based variations in rainfall, are generally a reflection of convective processes or thunderstorms. When I talk about convection and thunderstorms in this talk, we can use those words more or less interchangeably. You can have convection and rain without thunderstorms, of course. So basically this tells us that to understand precipitation in a warmer world, we have to understand thunderstorms and convection in a warmer world. So thunderstorms, as we know, are a meteorological hazard. We get thunderstorms when we have an unstable environment, warm air underneath cool air, so when we get a buoyant surface parcel, which is caused to lift by a source of lifting, such as topography or sea breeze convergence or thermals over the land during a hot day, or rising air ahead of a cold front. Combined with that unstable atmosphere, then we get a buoyant surface parcel. When it begins to rise in a humid environment, then we get condensation, latent heat release, which contributes to the buoyancy of the parcel, and we get a thunderstorm forming. Now, if we also, so the hazards that we can get forming with a thunderstorm are tornadoes, flash flooding, large hailstones, and damaging winds. Now, precisely which ones of these thunderstorm hazards we might get forming is quite dependent on the subtleties of the wind and moisture profiles. So here's a picture of a thunderstorm. So we have these buoyant updrafts here and rainfall falling out of the storm here. Now, this is a very simple diagram, but in a regular thunderstorm, once we get rain starting to fall out of the thunderstorm, then it will cut off the source of buoyant warm air and the thunderstorm will naturally dissipate. In an environment where we have a high level of vertical wind shear, so that's wind that changes strength with height, then the whole thunderstorm can become tilted over. And what this means is that the location where the rain is falling is geographically displaced from the source of warm, moist air into the thunderstorm, and this is where we can get a severe thunderstorm forming, and the thunderstorm can become much more long-lived, and it's more likely that we can see things like tornadoes and large hail arising out of the thunderstorm. And also in a sheared environment, it's more likely that we can see the thunderstorm getting organised into a big area of a big organised area or squall line of thunderstorms, which we can call a mesoscale convective system. So we can see from this that the two things that are really important for understanding if a thunderstorm will form are the instability and the vertical wind shear. So here's the problem in understanding thunderstorms in a future climate. Here's a GCM grid box, and here's a thunderstorm. So a GCM grid box might have a size of, 50 to 200 kilometres, and a thunderstorm has a scale of around 10, in the order of 10 kilometres. And even a big organised area of thunderstorms might have a size of 100 to 200 kilometres, which still is scarcely fitting within a GCM grid box. So thunderstorms are simply not resolved in most GCMs. So to look at how thunderstorms might evolve in a future climate, most studies have taken the approach of making projections of thunderstorm environments. So we can't model thunderstorms themselves, but we can model the instability and vertical wind shear that will lead to the formation of thunderstorms. The instability is has generally been assessed for thunderstorms using the convective available potential energy, which is the vertically integrated buoyant energy available to lift a parcel of air in a conditionally unstable atmosphere. And the vertical wind shear, which makes it more likely to get a severe thunderstorm, which is obviously just the difference in wind speed between two particular heights in the atmosphere. So let's just have a look at how CAPE might change in a warmer world. So I'm showing here a profile of temperature and dew point temperature. It's a randomly chosen profile from Brisbane Airport. And shown in grey here is the trajectory taken by a surface parcel lifted from down here, following first a dried adiabat, and then once it becomes saturated, following a moist adiabat. Here is where the parcel becomes warmer than its environment, so it's positively buoyant, and it's going to lift until it becomes cooler than the environment again. And this area in here is our convective available potential energy. Now, if I just warm the surface by a few degrees, so if you look down here as I go to the next slide, I've warmed the surface a little bit, and my CAPE's gone from 640 to 1086 joules, so I've already got a more intense thunderstorm. Now, this is simplistic because it's not just the surface that warms, that will warm, and if we get warming in the troposphere as well, through here, then we'll decrease the Cape again. Now, let's have a look at moisture. So instead of increasing the surface temperature, I'm now going to increase the moisture at the surface by increasing the dew point temperature. And then I get a really enormous Cape. So I guess this is just a conceptual model of how the Cape might respond to increasing temperatures and moisture. But in reality, in a GCM, we can directly take profiles like these of temperature and potential dew point temperature and calculate what the Cape might be explicitly. So there's been a bunch of studies that have looked at how Cape and shear might change in a warmer world. And these studies have all followed a fairly similar path in looking at Cape and shear in GCMs. So starting with Trapp et al. In 2007, found a net increase in severe thunderstorm environments in the continental US, due mainly to increased water vapour in the PBL. So we saw what increased moisture can do to the Cape. Brooks, 2013, projected that Cape would increase, but shear would decrease. So this is a trade-off. We've got more Cape, making it more likely to get thunderstorms, less shear, making it less likely to get thunderstorms. But overall, he predicted more frequent thunderstorm environments, but that the impact of hail and tornadoes, so the specific hazards, was really uncertain. He also urged caution in interpreting observational records of thunderstorms, because these specific hazards are really difficult to observe, and if there was no one there, then it's not going to be reported as having happened. Then moving on to Australia, Allen et al. Looked at two climate models and projected significant increases in thunderstorm environments for northern and eastern Australia. And he also said this was a response to increasing Cape from high continental moisture. And he also said that decreases in shear were not large enough to offset increases in Cape. And he projected potential thunderstorm days increasing by 14% in Brisbane, 22% in Melbourne and 30% in Sydney. And then a final study I've got here, Paquin et al. 2014, Cape expected to increase over the US, whereas shear is expected to decrease. And severe precipitation events may become more frequent and slightly more intense. Now, this decrease in shear that a number of people have reported has been attributed to a decrease in the horizontal temperature gradients, which has therefore decreased the vertical wind gradient. So I'm just going to go through a couple of these studies. So this is some results from the Trapp et al. Study, where he has compared the late 21st century to the late 20th century. And this is convective available potential energy in summer over the United States, a big increase over here, shear, a big decrease over here. Noted that they're not actually co-located. Putting these together, he defined an increase in severe thunderstorm environment days over the summer as increasing throughout much of the eastern United States. This is the study by Allen et al. Together with David Carley and Kevin Walsh, looking at two climate models and defining a mean severe environment difference. You can see that there's a really large uncertainty, so a really big difference between these two models, but they both have some kind of similar trend of an increase in severe thunderstorm days up the east coast of Australia. Okay, so there's also been a number of studies looking at how the increasing variability of rainfall can be related to an increase in severe convective events. So this was a study looking at the observed changes in extreme wet and dry spells during the South Asian summer monsoon season. The South Asian summer monsoon is really important because there's a lot of people living in the region depending on this rainfall for their livelihood or alternatively being affected by flooding. So this study found decreasing mean rainfall but increasing day-to-day variability. And they also detected a small increase in the tail of the rainfall distribution, which they attributed to more heavy events. So we had both this, although we had a decrease in mean rainfall, we had increasing variability. And this actually really matters to how the rainfall is experienced. So a few isolated events of very heavy rain are much less useful than an extended period of lighter rain, because lighter rain, I think Andy talked about this yesterday, a long period of lighter rain is more likely to soak into the into the soil, whereas very heavy rain is likely to just run off and may also cause flooding. So a simple number on how much the rainfall might increase in a region is actually not that useful. We need to know what type of rain it is and what kind of distribution it will have. So this study also attributed the increase in day-to-day variability to an increase in CAPE and an increase in low-level moisture convergence, with wet periods becoming wetter but less frequent and dry periods becoming less dry but more frequent. Okay, so these studies that have looked at CAPE have all looked grid point by grid point at how likely it might be to initiate a thunderstorm. But an added level of complexity is that thunderstorms tend to organise themselves into large mesoscale convective systems. So mesoscale convective systems is the upscale organisation and aggregation of thunderstorms. And anything where we see the word upscale is a flag to be something where these small-scale processes might actually feed back onto intraseasonal or even climate scales. So MCSs are long-lived and responsible for flooding, hail, strong winds and tornadoes, and they were defined by Howes as any cumulonimbus cloud system that has a continuous rain area of 100 kilometres or more in at least one direction. And this study by Nesbitt et al. Found that MCSs are responsible for over 50% of rainfall in many areas, particularly in the tropics. So anything that's responsible for over 50% of rainfall is clearly worth careful consideration in a future climate. And this was the result from Nesbitt et al. He used satellite-derived estimates of precipitation to show the percentage of the fraction of rainfall derived from MCSs. And you can see that right through the tropics, we've got numbers often greater than 0.5. This was another study showing a similar thing. Just looking at the bottom figure here, we've got the percentage of rain derived from systems with a size greater than 250 kilometres. So a similar result, really large percentage of rain derived from these big, organised, intense precipitating systems. So within a big area of rainfall, within a big organised area of convection, it's not just non-stop thunderstorms going on. We've got different physical processes. So within this thunderstorm area, we're going to have convective cores where we've got very strong updrafts, possibly separated by areas where there's no rain. And then when we've got the thunderstorm anvils spreading out, we're going to have areas of stratiform rain. So stratiform rain is going to be a bit lighter but heavy set-in kind of rain. And within a mesoscale convective system, there will be both areas of convective and stratiform rain. Now, this is important not only for how we experience the rain at the surface and how much rain actually falls, but these different types of rain actually have fundamental different feedbacks onto the atmosphere. So in a convective cloud, we have deep heating all the way through the atmosphere due to the latent heat release in the updraft. Whereas in a stratiform cloud, we've got a thick layer of cloud here where we have latent heat release, so heating. Underneath, where there's no cloud but we've got rain, there's evaporation and cooling. So depending on the type of rain we have, we've got different feedbacks to the atmosphere. And remembering that this whole thing still fits well within the grid box of a GCM, or maybe approaching the size of a GCM grid box. So this is a schematic of the latent or diabatic heating that we might experience in different types of cloud or different types of rainfall. So this is the stratiform rain here, where we've got heating aloft and cooling below. And here's the convective cloud, where we've got deep heating right the way through the atmosphere. And this schematic here shows the amount of the overall heating we might get from a whole MCS, depending on the percentage of stratiform rain that we have within the MCS. And you can see really different amounts of heating depending on the makeup of that cloud. Now, in the tropics, the primary, at least in the tropics to the north of Australia, the primary mode of intraseasonal variability is the Madden-Julian oscillation. This is a satellite picture. This is the edge of Australia here. So this is the Indian Ocean here. And this is a picture of the Madden-Julian oscillation moving over the region. So the Madden-Julian oscillation has a period of 30 to 60 days, and it propagates from the Indian Ocean to the Central Pacific. And it's associated with this big blob of cloudiness and convection moving over the region. Now you can see within the intraseasonal variability event that it's not just one continuous area of rain. We've got areas where there's clear kind of intense convection, and then filled in between with general cloudiness. And so within this area, there's a great deal of variation in stratiform and convective cloud. So it turns out that the MGO is really, really difficult to model in global climate models. This is a little Hofmöller plot up here of the observed MJO. So we've got longitude along the horizontal axis and time in days along the vertical axis. And this is 20 to 100 day filtered rain anomalies. So this is an MJO event here, propagating through the maritime continent region, or actually from the Indian to Pacific Oceans. And this is the same thing in a whole group of global climate model hindcasts. And there were a lot more in the paper as well that all looked equally bad, but I just took a selection here to show you that this feature is either not modelled at all or modelled extremely poorly in GCMs. And it's not really understood why, but the hypotheses that have been put forward for why the MGO is not modelled well in global climate models are relating to the diabatic heating and the moistening that is going on within the rainfall in the region. So these cloud processes really, really matter, not just for the local experience of what happens with the rain, but for their upscale impact onto intraseasonal variability. And as the major mode of variability in the maritime continent region, which is essentially the rainiest area on the planet, I would argue that this also matters for understanding the climate generally. So this is from a high-resolution model which does resolve stratiform and convective rain, and it is the ratio of stratiform to convective rainfall over Sumatra during the MGO active versus the MJO suppressed phases. And so we can see that when the MJO active phase is over us, we've got a much higher ratio of stratiform to convective rain than when the MJO is not over the region, where we've got a much lower ratio of stratiform rain, and it's basically just the convection being driven by the topography and coastal effects. So we can see that this ratio of stratiform to convective rainfall is fundamentally caught up in how the MJO propagates, and there's this two-way interaction between the intraseasonal variability and the local scale effects. This is another illustration of how the problems in simulating the types of rainfall in the tropics. So this shows up here the multi-model mean precipitation from 32 historical CMIP5 models. And this is the same result from a satellite precipitation estimate. So you can see that the mean precipitation is not too bad at all. But when we split that up into the percentiles of rainfall from the 25th up to the 99th, we can see that the global climate models have got a great deal more of the rain coming from light rain, whereas the satellite precipitation estimates have got most of their rain coming from heavy rain. And that is the convective rainfall that is simply not there in the GCMs. So this doesn't necessarily impact our ability to get global mean rainfall correct, but it does impact on the types of rain. Okay, so I'm now going to talk a little bit about one region where the inability of global climate models to capture mesoscale convective systems has been attributed to overall errors in the prediction of climate variability. So I'm going to talk about this region here, the Sahel. So in this region we've got the Sahara Desert to the north, and then this region here has been affected by periodic periods of really, really severe drought and famine, and as such it has received quite a lot of attention in the scientific literature. So there was a study came out this year, which showed an observed increase in West African mesoscale convective systems, despite the fact that there was no observed increase in surface temperatures. So, and this was attributed to the increased horizontal temperature gradient from Saharan warming to the north, leading to increased vertical wind shear. So this was the annual rainfall that has been increasing through this period here, with a great deal of interannual variability. And this is the contribution of extreme events to the annual rain. And so this is the extreme events coming from the mesoscale convective systems. So this is the Sahel region here, and this is the observed change in temperature. And you can see that there's not really any observed change in temperature in this region itself. On the other hand, to the north, in the Sahara Desert, we have strong observed increases in temperature. So this uneven increase in temperature has caused an increase in the vertical wind shear, which in this paper they were arguing that it's the increase in vertical wind shear that has caused the increase in mesoscale convective systems, which has caused the increase in rainfall. And so it's the cause of the MCSs is actually geographically displaced from where we've seen the effect. And they wrote in their conclusions that they found that existing GCMs cannot reproduce the observed rate or spatial pattern of extreme rainfall intensification, presumably in part because they cannot capture key physical processes responsible for organised convection. Now, they also said that as the world continues to warm, we may find rapid MCS intensification signals emerging in other regions in the world where the Clausius-Clapeyron relationship and indeed present GCM extreme rainfall predictions are of little value. Now, there was another Nature paper shot back a couple of months later urging caution on this and saying that that was a bit too strong a statement, and to say that to go beyond speculation, we need to understand the distribution and characteristics of extreme precipitation events across many different regions because of the substantial regional variations in how the atmosphere responds to the changing climate. So I guess this was just one region, and I guess the Liu et al. Paper was saying we need to do these kind of studies in other regions as well to make more general kind of comments. So still on this Sahel region, this is a modelling study using the UK Met Office model, trying to look into why models are not really capturing the rainfall in the region. So this is a Hofmöller plot again, with longitude here and time going downwards here. This is satellite precipitation estimates, and we can see that we've got this diurnal cycle in rainfall, but also this organisation and propagation of mesoscale convective systems from east to west, occurring consistently during the period. Now, this is the model that had a horizontal grid spacing of 130 kilometres, and basically in this model we just saw no convective organisation at all, but we just had rain popping up everywhere at the same time every day. So basically the sun would come up and the model would do convection and rain, and then it would stop again. In their version of their model that they ran at 25 kilometres, which they said was much better, we see a sign of convective organisation, at least, even though it's kind of completely wrong, but at least there's convective organisation going on. But we still see this sort of diurnal cycle popping up everywhere at the same time, every day, instead of the organised systems that we see in the observations. So despite the fact that it seems like the organisation was still quite wrong, it did make a big improvement. So here, this is the observed rainfall trend in the blue colour up here. And then the model resolutions, this is the coarse one in green, and then going to higher resolution and higher resolution again in orange. So this 25-kilometre model did make really significant improvements in the total amount of rainfall and, importantly, in the trend. Now, they broke this trend down into the contribution to the trend from weak rainfall and the contribution to the trend from strong rainfall. And you can see that there's hardly any trend in the weak rainfall, but almost all the trend comes from the strong rainfall or the kind of organised convective events. And in particular, the slope of this trend increases when we decrease the model resolution. Okay, so model resolution is clearly one really huge issue when it comes to simulating convection and thunderstorms, because we basically need to fit the storm within a grid box, or the storm needs to cover several grid boxes to have any chance of being resolved. But the other major issue in the modelling of convection and thunderstorms is the convective parameterisation in the model. So large-scale climate models that cannot explicitly model storms have to have a convective parameterisation to adjust the atmosphere to account for the impact of that unresolved convection. Now, the convective parameterisation can work in a number of different ways, but I guess two of the major classes of convective parameterisations either calculate adjustments to heat and moisture and pull them back to a reference profile based on a convective triggering function. So the model notices where it's about to do convection and then takes that moisture out of the atmosphere and adjusts the heat and moisture profiles to what they would have been if the convection had happened. Or then we've got another class of convective parameterisations, which is based on balancing the mass in updrafts and downdrafts in convection, but again based on a convective triggering function. And this convective triggering function is actually one of the fundamental pieces of the puzzle when it comes to convective parameterisations. So looking at the impact of the convective parameterisation, this is a study, again using the Met Office, the UK Met Office model, with a horizontal resolution of 17 kilometres. Now, normally you wouldn't run a 17-kilometre model without a convective parameterisation. We could normally start turning off the convective parameterisation and letting the model physics do the convection by itself at a resolution of more like 4 kilometres. But anyway, they looked with a resolution of 17 kilometres, and this is the time of day when the precipitation reaches its peak. So we know in the tropics it rains in the afternoon and evening. I think anyone who's been to the tropics knows that there's a thunderstorm in the afternoon or evening almost every day. And so this is the observed time of the peak precipitation, and this is the same result from a model with a convective parameterisation. So you can see that it's not doing anything like what it's supposed to do, and basically it's just raining way too early in the day, because it's the same thing that I showed before of the sun comes up and it rains, and that's it. And so then this is their model where they turn their convective parameterisation off and let the model develop its own convection. It looks a little bit more like the observed version, although we still don't have this kind of organisation around the coasts. Now, in this study, they showed how when we had parameterised convection, the rain occurred too early in the day. When the rain occurred too early in the day, then we had too much cooling of the land surface. If we had too much cooling of the land surface, then the sea breeze didn't develop as much as it should, because we didn't have enough land-sea temperature contrast. And when we didn't have enough sea breeze forming, then we had a damping of the convection that was forming in the afternoon because we didn't have as much convergence from the sea breeze. So I think this is a really nice example of how errors in the convection flow on to other aspects of the mesoscale dynamics. Okay, and then there's a study recently come out by Kendon et al., which looked at which atmospheric phenomena we might require a convection permitting model to simulate properly, and which phenomena could be adequately resolved in a GCM. And so she's looked at seasonal mean precipitation, wintertime precipitation intensity, and rainfall event occurrence. She said that we've got quite good confidence in coarse resolution regional climate projections, whereas for things like fog, lightning, hail, severe convective wind gusts, short duration rain extremes, and summertime rainfall intensity and duration, then we need to have a high resolution model that is resolving those mesoscale kind of dynamics. Now, this paper, interestingly, didn't really talk very much about the tropics. And I think the tropics is a region where it might, and I'm saying it might because I don't know, but I think the tropics is a place where we have to be really careful about seasonal mean precipitation because of the impact of intraseasonal events, which are quite driven by the mesoscale dynamics and the diabatic heating. Okay, so given these issues, and given that we can't at this stage run global climate models with convection permitting resolutions, what can we do? So we can try to run at a high enough resolution to resolve the convection. We can run with a super parameterization, or we can invent new parameterization schemes. So in Japan, they have really enormous supercomputing power. So they did run their global climate model with explicit convection, so without a convective parameterization. And in this model, they ran at 14 kilometres, so still fairly coarse to be running without a convective parameterization. But they tried to simulate the MJO with this model, and they did a really, really good job. So this is a Hofmüller plot. We've got observed outgoing long-wave radiation and observed precipitation, and simulated our OLR and precipitation. And you can see the propagation intensity and speed and the size of the structures all look really, really good. Now, they also tried to run their GCM with horizontal resolutions of 14, 7, 3.5, 1.7 and 0.87 kilometre grid spacing. And with these grid spacings, they managed to run their GCM for 12 hours. So 12 hours is clearly not long enough to say very much about the future climate. But they did use their study to draw some really interesting conclusions about what's happening with the scales of the clouds and the types of clouds as we decrease the model resolution. So these are just some beautiful, cloud pictures from their models. This was the 0.7 kilometre resolution one here. You can see that there's much more fine detail, and they didn't say much about this, but interestingly you can see that there are whole features in different places in their different resolutions. But they were mostly looking at the globally averaged properties of the convection in their model, and looking at how they converged as they decreased the model resolution. Now, this is their outgoing long-wave radiation. This is observed in the dashed black line, and then we're going from coarse resolution in black through to fine resolution in red. So the OLR didn't quite converge as we decreased the resolution. So we've got less OLR, so less cloudiness altogether, when we've got the very high resolution. On the other hand, they counted the number of convective cores in their model, and this is definitely not converged. So we've got many, many more, globally, we've got many, many more convective cores at that very fine resolution. Now, that might not necessarily matter if we had two small convective cores doing the same thing as one big convective core. However, and and indeed it didn't matter when they looked at precipitation. So this was the global average precipitation rate in millimetres per hour at their different model resolutions, and it's converged almost exactly, which is very encouraging for kind of predictions of global precipitation. But what they did look at here is the proportions of the globe covered by different types of clouds. So this grey here is the amount of clear sky. Red is the amount of deep convection. Green is cirrostratus. Blue is light blue is cirrus. Orange is middle level cloud, and blue is low cloud. So the amount, the cloud areas and the cloud types definitely didn't converge. And so this is the amount of deep convection. So the amount of deep convection, the amount of the globe covered by deep convection actually decreased, but that meant there must have been heavier rain going on where there was deep convection. So we're talking about greater rainfall extremes. And they also had a greater area of cirrus clouds, which they attributed to better resolved anvils connected with that convection. So I think this is a really fascinating study, and I think one of the most fascinating things is that it looks like it still hasn't converged at 0.87 kilometres. Okay, so this was a really fascinating study, and I guess it taught us a lot of things, but it's probably not practical for moving forward with climate simulations at the moment. So another approach here is to work with the superparameterization, and a superparameterization is where inside every grid box of a GCM we have nested a two-dimensional cloud resolving model. So for all the processes that we don't need that fine scale resolution, we can do that at the GCM resolution, and then we do the cloud stuff at the small scale resolution. And I couldn't find, unfortunately, a plot of the MJO propagation in a superparameterized model, but this does look at, this is basically a Hofmöller plot in spectral space with wave number and frequency along the two axes, and this is the observed MJO down here, so with the first few zonal wave numbers and timescales slower than 30 days. This is in a non-superparameterized model, so the MJO is basically more or less missing, and this is the MJO in a superparameterized model. So it's been shown big improvements in the representation of the MJO in these superparameterized models. So by way of summary, convection matters. It plays a critical role in the current and the future climate. There are many aspects of convection that are not captured in GCMs. The precise phenomena arising from severe thunderstorms are really highly sensitive to the CAPE and shear. And I think even in these studies where they look at the large-scale CAPE and shear from a climate model, there's probably missing a lot of the sort of regional variation in those variables. Then the partitioning between convective and stratiform rainfall is really critical for the upscale diabatic heating, the latent heating effects. And I guess in the future, GCMs ultimately will be convection permitting or superparameterized or have some brand new convection scheme that someone will invent. So, thank you. Yes?
So you said that about 4 kilometer resolution is necessary for resolving convection. Is that a latitude dependent?
That's a really good question. I don't know. I guess convective systems tend to be a bit larger in the tropics, so maybe there might be a slight difference. But
I'm just thinking of like ocean eddies are smaller and higher latitude, just from the rise being radius. So
yeah,
depending on the rise of the radius. So.
I don't think. I'm not an expert in this, but I don't think that there's as much variation in the size of convection as there would be in ocean eddies. Yeah, good question.
that you talked about in the...
Or it's a local circulation. I'm not an expert in it, but it's a local circulation that's responsible for a great deal of rainfall in this region. And yeah, it's typically really difficult to model. So, yeah. Oh, yes, hello.
How long was the 14-kilometre Japanese GCM run for?
The MJO one or the outer nest of the nested ones?
I think the MGO. Yeah, that one.
That one? Yeah, I'm not sure. They might have just run it for this particular MJO event.
Okay.
Yeah, I think it was a process-based one where they ran it.
But there was one that was a GCM, right?
Yep.
Does that
Yep.
mean it was done globally?
Yes, so these models were all done globally. And the way they did it was that they started to run the 14-kilometre one and they spun that up, and then they put the 7-kilometre one in, and then spun that up, and then put the 3.5 one. And so they sort of ran each one for 12 or so hours and then put the next resolution in. So I think the 14-kilometre one might have run for a few days, but then the final 0.87 one was only 12 hours.
Do you have any idea how much longer or slower a model with super parameterizations would be versus just regular parameterization?
Yeah, I don't know how much longer, but it is significantly more computationally intensive. Yeah. Yeah.
There was a plot with several MJO in different models.
Mm-hmm.
And I think there was one that had an atmospheric model only, and then there was a coupled model, and it was much better in the coupled model. But I always thought that the main idea was that MJO is almost an atmospheric only process.
Mm.
Is it? Can you explain why it's much better in the coupled model?
No, I can't. Sorry.
In your view, how important do you think is the role of the land surface in us getting these kinds of storms right in climate models? And are we only going to see how important that resolution?
In climate models, I think getting the land surface right is probably necessary but not sufficient to get the convection right. Like if you had completely the wrong type of land surface, then you're responding to surface heating in different ways, and this, in the end, this is all about surface heating, initiating convection. But simply fixing the land surface is not going to be enough to fix the convection. Yeah.
Okay. Thank you, Claire.